So we talked about the axon hillock was where the threshold tends to be slightly lower at the axon hillock. The equations for the sodium activation are slightly different. They're shifted just a little bit in their voltage sensitivity. One thing I really should point out is if this V is equal to minus 35, what happens in this equation? What happens? So, yeah? It's undefined. Why is it? So this becomes, that becomes 1. That's right. It becomes 1 minus 1, 0. 1 over 0 is infinity. So there's a pole in these equations, right? And you'll find in almost all the alphas there's some kind of pole in the equations. And the poles are a real pain in the ass. And so you need to use special integrators in order to run these equations, because what will happen is you'll get a value at some point very close to positive 35 millivolts, and the equations are going to explode on you. And you have to have an integrator that can deal with those explosions. And MATLAB has a nice integrator, which is called ODE 15S. And the S is for stiff. And the stiff allows you to deal with the poles in the equation. And once it sees something explode like that, it figures out how to step over it correctly. So you can't use just any integrator when you're running these things. It may run for a little while, but you must use the ODE 15S or the 23S integrator when you run these homeworks if you want it to reliably run for longer than like a second. Okay, so we talked about an action potential now we can think of as actually moving along a cable down an axon. And if we think about an axon, we can think it about as a cable. And there is a resistance going along inside it, which is, we're going to call this RL. And then there's going to be a resistance going across the membrane, which we'll call RM. And there's a capacitance that goes across the membrane as well. Right? And the capacitance and the resistance and along these things depend on the size of the axon. So if we think of the A as the radius of the axon, we can think of as we can think of as a patch of membrane. So RM, which is resistance per centimeter squared or something like that. RM is equal to, so the larger the area, the smaller the resistance is, right? So the RM, the membrane resistance is going to be equal to the membrane per area divided by the area. So it's going to be 2 pi A. Whereas the capacitance goes up. So we're also going to have a capacitance. Capacitance is capacitance per centimeter squared is going to be equal to Cm times 2 pi A. And the axial resistance, the smaller the the axis, the smaller the diameter of the axon, the higher the resistance is going to be going along that direction, right? So the RL is going to be 2. So if we think about area inside, this is RL per centimeter squared. This is thinking about the resistance of the fluid inside. So there's resistance across the membrane, and there's resistance along the fluid inside the cell. That's the axial resistance, which is going to be divided by pi over A squared, because as the radius gets larger, the membrane surface goes up linearly, but the area goes up as a square. Right? So what we'll find is how quickly an action potential travels down an axon will depend on sort of the ratio of the axial resistance to the membrane resistance. The lower the resistance is across the membrane, the more current is going to go out the membrane rather than down the axis, right? Which means it's going to decay faster as you move down with distance, right? So this is just the passive properties of this axon, the cable properties. And so with a bigger radius, it turns out it'll travel down faster because this resistance ratio compared to the membrane ratio is going to be smaller, or it's going to be, well, it's going to be larger. Depends what sign you use. But so it's going to go down faster. So there is what we call a time constant. So if we were changing the voltage at a particular point in space, how quickly does it return back to the resting potential from that perturbation? That's the time constant. And then we're also perturb it, and it's going to move along the axon, and we're going to ask how far does it travel before it decays to a point where it's some size smaller, and that's going to be the length constant. And so I'm just going to write down the equations here. The length constant, let's see. dV dx, dt equals V. So we can look at the voltage at some position, and that's going to be dependent on space. So this is called the length constant. And this one is called the time constant. And the length constant is equal to lambda is equal to the square root of the ratio of the resistance across the membrane to the resistance along the axis. And that's equal to square root of, if we write it out explicitly, Rm over Rl times the diameter over 4. And the time constant, tau, is equal to the resistance to the membrane divided by the capacitance of the membrane, just like an RC circuit.